Hey guys, this video is going to be about energy, wavelength, and frequency. So if you remember, this is the symbol for wavelength. It is the Greek letter lambda. And then this is the symbol for frequency. It's the Greek letter nu, N-U. And then this, of course, is energy. So we are going to see the relationships and how all these are interconnected together, and a couple of questions that kind of tell you what kind of calculations you might need to do with them. All right, so the equations that we're going to talk about is energy is equal to H nu, and that is where E is energy, and it's usually measured in joules. So if it's given to you in kilojoules, you have to convert it to joules before you plug it into this equation. Planck's constant is H, and it is 6.626 times 10 to the negative 34 joule seconds. And then frequency is nu, and it is inverse seconds or hertz. So if we look at a wave, right, frequency is how often the wave cycles in a given amount of time. And then wavelength down here is the distance between two peaks. C is the speed of light, 2.998 times 10 to the 8th meters per second. So wavelength and frequency are then related to each other by the speed of light. So this only works within the electromagnetic spectrum range. So for sound, if you wanted to do these calculations for sound, you'd have to use the speed of sound, not this is the speed of light, because we're talking about different types of light here. So if we want to calculate the frequency and the energy of blue light that has a wavelength of 400 nanometers, so this is just a very simple calculation. So our wavelength is 400 nanometers, and we want the frequency, and we also want the energy. So I'm going to calculate frequency first. So the relationship between wavelength and frequency is C is equal to wavelength times the frequency, and C is 2.998 times 10 to the 8 meters per second. And that's going to be equal to the wavelength times the frequency. So since our C is in meters here, then that means this has to be in meters. So I'm going to first convert this to meters. So if I have 400 nanometers, there are a billion, or 1 times 10 to the 9th nanometers in 1 meter. So that's going to be 4.00 times 10 to the negative 7 meters. So I'm going to plug that in for wavelength, because it's the length of the wave. It's measured in meters. And then my frequency will be nu. So this is meters. So then I'm going to divide by 4 times 10 to the negative 7 meters. Okay, and then meters will cancel out. So if I take 2.998 times 10 to the 8th and I divide by 4 times 10 to the negative 7th, I end up getting 7.5 times 10 to the 14th. My units are inverse seconds. So inverse seconds is the same thing as hertz. So you could also say 7.50 times 10 to the 14th hertz. All right, and so for energy, I'm going to use this relationship, and I'm going to plug in 6.626 times 10 to the negative 34 joule times a second. And my frequency is 7.50 times 10 to the 14th inverse seconds. So then seconds cancels out. And when I multiply these two in the calculator, I end up getting 4.97 times 10 to the negative 19 joules per photon. So a photon is a particle of light. So one particle at this wavelength will have that energy. Only one particle. So we're only calculating for one photon here. All right, so electronic transitions. So when light of a particular wavelength is shined onto an atom, its electrons can absorb a photon of that light and move to a higher energy level. So we've already looked at ionization energy and the photoelectron spectroscopy. So we know that if we focus a particular light on something, we can actually remove the electrons. But really what we can do is we can make an electron within the first energy level go up to the second energy level. But then it has to come back down. And when it comes back down, it's going to release the same amount of energy that it had to absorb. When electrons absorb energy, it has to be the exact amount of energy. It can't be less than that. So it can't go from n equals 1 to n equals 1.5. It doesn't exist. It has to be at least this much energy or it won't absorb the energy at all. All right, so it's kind of like climbing a staircase. You can't go in between the stairs. You have to hit each level before you can go up to the next. And if something is going to go from n equals 1 to, let's say, n equals 3, it has to absorb more energy. And this graphic really isn't very good because it doesn't show you that each energy level, as you move further out, they actually get closer together. So n equals 3 is going to be closer to n equals 4 than it is to n equals 2. And so they get closer in energy as they move further out. And it says the further the electron moves, the more energy is absorbed. So if it's skipping 2 or 3 levels, then that means that it's absorbing more energy. And so going from n equals 2 to n equals 3 is going to be less energy than n equals 1 to n equals 2 because 2 to 3 is closer together than 1 to 2. I hope that makes sense. All right. So let's look at some examples of this. Okay, of the following transitions in the Bohr hydrogen atom, the blank transition results in the emission of the highest energy photon. So the only time it's going to emit photons of light, right, is if it's coming down in energy. So n equals 1 to 6 is not going to emit photon. It would have to absorb it to do that because it has to go to a higher energy level, so it needs energy to do that. So that is definitely not the answer. 3 to 6, it would have to absorb. 1 to 4, it would have to absorb, right? So, and highest energy is going to require the greatest jump. So 6 to 1 would be the greatest jump. 6 to 3 would require energy to be emitted, but it wouldn't be the biggest difference. All right, the next question, which of the following electronic transitions in a hydrogen atom would have the longest wavelength? So this is a very similar question, but we need to know how they're related to each other. So energy is directly related to frequency. Okay, so if energy goes up, the frequency is going to go up. But frequency and wavelength are inversely related. So that means that wavelength goes up, energy goes down, and frequency goes down. And we can look at that if we just compare two. So pretend it actually looks like a real wave and it's not just some kindergarten drawing. But this is going to have a shorter wavelength, so the wavelength will be smaller, but it's happening more frequently, so a higher frequency and a higher energy when compared to this one, where this has a longer wavelength, but it's lower in energy and lower in frequency. So that just shows you that if this gets bigger, these get smaller, and if the wavelength shrinks, then the frequency and energy go up. All right, so which of the following electronic transitions in a hydrogen atom would have the longest wavelength? So if we want the wavelength to be long, then that means we're looking for the smallest energy. If we're going to compare 4 to 1 and 4 to 2, well, 4 to 2 is going to be a lower energy than 4 to 1. So that means that it's going to be a higher wavelength. Right? So we're looking for lower energy. So I'm just going to write that out here, lower energy. Okay? And then we can compare 4 to 2 and 2 to 1, which could be kind of a draw. But then we have this 4 to 3. Well, remember, if this is n equals 1, and this is n equals 2, and then this would be n equals 3, and this would be n equals 4. They get closer together as we go higher. So the 4 to 3 is just one level difference, but since they're higher in energy, it's going to be closer, and so less energy than the previous one. So this one would have the longest wavelength because it's going to be the smallest amount of energy. All right, and then the last example says the minimum energy needed to break an oxygen-oxygen bond in ozone is 387 kilojoules per mole. Does a photon with a frequency of 1 × 10 to the 15th have enough energy to break this bond? Support your answer with a calculation. All right, so I am going to first find the energy required to break this bond. And so energy and frequency is related through this equation. And so my energy would be 6.626 times 10 to the negative 34 joule times a second. And then I'm going to multiply by 1 times 10 to the 15th seconds, inverse seconds. So seconds will cancel out. And then my answer here is 6.626 times 10 to the negative 19 joules, and that's per photon. Okay, so this is given to us as 387 kilojoules per mole. So I need to change this to moles. So if we have a mole, there are 6.02 times 10 to the 23rd photons per mole. Or you could say 6.02 times 10 to the 23rd photons per mole of ozone. So that is going to give me 398,885.2 joules per mole, or 399 kilojoules per mole. So since this exceeds this, then yes, it would have enough energy. Okay, so there would be enough energy to break the oxygen-oxygen bond in ozone.